Hello, and welcome to Sleep Gravity. There are nights when everything around us begins to slow down, and darkness no longer feels heavy. It becomes only a soft silence, a place where vast thoughts can pass through without disturbing sleep. In that quiet, the universe appears in a different way, not as numbers too large to hold, or images blazing with light, but as a deep, distant, and peaceful space, where some regions are dark not because they are empty, but because light no longer has a path back. Black holes belong to this kind of darkness. They are no longer an entirely unfamiliar idea to us. We have heard about them in scientific stories, seen simulations of them, and learned that around them, light can bend, time can flow differently, and matter that comes too close may not easily return. But familiarity can sometimes create a quiet illusion that once we know the name of something, once we have seen its image and heard a few of its most striking features, perhaps we understand it deeply enough. With black holes, the opposite is closer to the truth. The more science observes from the outside, the more it realizes that the inside still lies almost beyond the reach of any story we can tell. Stars can orbit an invisible mass at the center of a galaxy. Gravitational waves can spread through spacetime after two black holes merge. The shadow of a black hole can be reconstructed from data gathered by telescopes across the Earth. All of these things show that black holes are real, that they have mass, that they exert influence, and that they can leave clear traces in the universe. But they are still like footprints around a closed door. We know something immense is there, but what lies behind the door cannot send its story back. At the edge of a black hole, there is a boundary unlike any wall in everyday life. There is no hard surface to touch, no shining shell to announce that everything has changed. Physically, it is the event horizon, where the paths that could lead back outside gradually disappear from the future of anything falling in. From the outside, it is like a line of silence. Light that crosses it does not return. Signals that cross it do not return. A story that crosses it can no longer continue speaking to someone standing outside. It is this silence that makes black holes deeper than the familiar image of an object that swallows everything. To say only that a black hole prevents light from escaping is to touch only the outermost layer of the mystery. What makes it one of the great questions of modern physics is that, inside that boundary, humanity's strongest theories begin to approach a place where even they are no longer sure how to continue speaking. General relativity once opened a beautiful way of seeing the universe. Space and time are not a rigid stage set in advance for everything to move upon. They can curve, stretch, and be reshaped by matter and energy. Through this view, humans came to understand why light bends when it passes near a massive object, why time does not flow in exactly the same way everywhere, and why the universe itself can expand. But when that same theory is carried into the deepest region of a black hole, its mathematical paths lead to a strange place. A point where density and curvature, in the classical model, become extreme, as though reality has been compressed into a limit that the current language of physics cannot fully preserve. That place is often called a singularity. The name sounds like a final period, but perhaps it should be felt more gently. In science, a singularity does not necessarily declare that the universe truly ends there. It can also be a sign that the map we are using has been pushed far beyond the region it was made to describe. A map may guide us accurately across oceans, mountain ranges, and cities, but if we reach a place where the paper begins to tear, we do not rush to conclude that the land ahead does not exist. We only know that we need a deeper map. What is strange is that this feeling does not appear only inside black holes. When humans trace the history of the universe back to its earliest moments, before stars, before galaxies, before even the familiar structures the night sky leaves in our eyes, the models also move toward an extreme region. The Big Bang was not a ball of fire exploding into a space that already existed. It was more like space itself once existing in a hot, dense state, then beginning to expand, carrying with it the matter, light, and time of the observable universe. When we go far enough back, that story also touches a place where familiar concepts can no longer stand easily. On one side is the black hole, where matter collapses under its own weight. On the other is the early universe, where everything once existed in a far denser state before expanding. These two images are not the same, and they should not be mixed together too quickly. But they both lead science to a very deep edge, where gravity, time, density, and the quantum world seem to need to meet inside a theory humanity has not yet completed. From that edge, a bold idea begins to find room to appear. What if, inside a black hole, collapse does not continue forever into a true infinity? What if, at extremely high density, some mechanism prevents matter from entering an absolute dead end, and instead carries it into another state of spacetime? In that case, what looks from the outside like a silent ending might, in a deeper model, be the hidden side of an opening. This idea is not a proven truth. No telescope has looked through an event horizon and seen a baby universe forming. No signal from inside a black hole has returned to say that another realm of space exists there. But the very fact that this question can be asked seriously is part of what makes black holes one of the strangest places in scientific thought. They force us to distinguish between what has been seen, what can be inferred, and what still belongs to the deeper, unfinished part of physics. Perhaps the inside of a black hole is only a state that future science will describe with more precise equations, without needing another universe at all. Perhaps models of a bounce, of new branches of spacetime, or of baby universes will turn out to be only temporary steps on the way toward a better theory. But in the darkness of a black hole, the question remains, quiet and immense. When a region of space closes itself off from our view, does its story truly come to an end, or does it simply leave the part of the universe that light can tell? Tonight, at the edge of that shadow, what matters is no longer only that a black hole swallows light. What matters is the silence behind it, a silence deep enough to make physics ask whether endings and beginnings are always as separate as we have imagined. The deepest dark regions of the universe do not need to shine on their own to be recognized. A black hole reveals its presence by changing the paths of everything around it. A star passing nearby no longer follows the simple orbit it once had. A cloud of gas, drifting too close, begins to heat up, spin faster, and glow in its final moments before disappearing from view. Light from behind it bends and distorts, sometimes forming strange arcs around a central region that emits nothing at all. And when two black holes merge in some distant corner of the cosmos, space-time itself trembles ever so slightly, sending a delicate ripple across the universe for millions or even billions of years. Through traces like these, black holes have moved out of the realm of imagination and into the realm of data. They are no longer merely sketches on a chalkboard or unusual solutions hidden inside equations. At the center of the Milky Way, stars orbit an almost invisible point at such tremendous speeds that their paths become a quiet testimony to a concealed mass. In more distant galaxies, the hot gas surrounding a black hole can blaze brilliantly before some of it crosses the final boundary. Here on Earth, extraordinarily sensitive detectors can register distortions far smaller than anything human senses could ever perceive, revealing that somewhere in the distant darkness, two dark regions collided and became one. These discoveries make black holes feel both closer and farther away. Closer because they have been measured through motion, signals, images, and tiny vibrations in space-time itself. Farther, because most of what we know still comes only from the edge. We observe their influence on things that remain outside. We measure how they pull on stars, bend light, heat matter, and ripple the fabric of the universe. Yet the deepest region, where every path of light turns inward, still sends back no direct image. You might imagine a very heavy object resting beneath a dark sheet of fabric. You cannot see its full shape, but every fold in the cloth slopes toward the same place. Set a small marble nearby, and it rolls along the curves. Shine a beam of light across the surface, and its path bends as well. Every sign tells you that something significant lies beneath the fabric. Yet the fabric still hides the part you most want to understand. For a black hole, that covering is not dark dust, a cloud of gas, or an overwhelming distance. It is woven into the very structure of spacetime itself. Outside the black hole, physics can still tell the story through light, motion, and gravitational waves. But the closer one approaches its boundary, the narrower the paths become for signals trying to escape. Eventually, no light can return carrying news from within. What is hidden is not simply beyond the reach of better telescopes. It is hidden because the universe has placed there a boundary deeper than any ordinary veil. This is what makes black holes different from most other dark objects in space. A cold cloud that emits no light can still be detected because it absorbs light behind it. A distant planet that does not shine on its own can reveal itself by tugging gently on its parent star or by blocking a fraction of starlight as it passes across our line of sight. A dusty region between the stars may seem obscure to the eye, yet at other wavelengths it gradually emerges into view. Beyond a black hole's event horizon, however, the problem is not merely the absence of light. The problem is that the return path for light has been erased from the future. When humans observe the shadow of a black hole, what appears is not the surface of an object. It is the trace of a boundary. The dark region at the center is not like the shadow of a sphere illuminated from behind. It is the place where light that might otherwise have reached us has been drawn into trajectories with no escape. Around that darkness, light from hot gas and from the space beyond is bent into strange forms, as though the universe is showing us the edge of something it does not fully allow us to open. What a black hole reveals from the outside is surprisingly little. A star has colors, size, chemical composition, temperature, age, and layers of complex activity within its atmosphere. A planet may have a surface, an atmosphere, clouds, ice, volcanoes, or oceans. But a black hole, viewed from afar in the simplest physical description, seems to reveal only a few major properties: its mass, its spin, and, in theory, its electric charge. All the richness of whatever once fell into it appears absent from its outward face. That simplicity does not make a black hole less mysterious. It makes it more mysterious. If a book, a star, a cloud of gas, a planet, or any other form of matter carries immense amounts of information and then falls across that boundary, where does the history of those things go? From the outside, the black hole does not retell every page. It presents only a form that is remarkably simple, remarkably dark, and remarkably silent. Yet modern physics is not comfortable with the idea that information can simply be erased from reality like writing wiped clean from a chalkboard. The question does not need to be answered yet, but it begins to weave a delicate thread connecting black holes to deeper mysteries involving quantum physics and information itself. A black hole is like a bell that does not ring with light, yet causes the surrounding space to resonate. Objects near it move differently. Streams of gas around it grow hot and spiral inward. Mergers cause spacetime itself to vibrate. Humanity cannot see the deepest core, but it still recognizes the presence of the black hole through everything whose path has been altered. That recognition is both certain and humble. Certain, because the evidence is too abundant to deny. Humble, because every piece of evidence stops at a boundary that ordinary observation cannot cross. From here, the black hole begins to become a question larger than itself. It does not merely ask where matter falls. It asks how far light can tell a story. It asks how information may be hidden. It asks whether the equations that describe the outside so well are still capable of describing the inside. More deeply still, it leads us to wonder whether a region cut off from view must necessarily be a region without a story. The shadow of a black hole is not merely a dark spot against the sky. It is the trace of a place where the universe becomes so private that all familiar ways of seeing must stop at the outer edge. Outside, there is still motion, light, heat, gravitational waves, and data for humanity to read slowly and carefully. Inside, there remains only a silence that physics has not yet been able to turn into a direct image. It is within that silence that our question truly begins to gain depth. Near that shadowed region, light does not strike a wall. It is not extinguished like a candle in the wind. It simply follows paths for which none lead back to the observer outside. To understand why an invisible boundary can lock away an entire part of the universe's story, we need to move closer to what is known as the event horizon, not as an imagined gate, but as the dividing line where the future of light itself begins to change direction. Near a black hole, the first thing that changes is not necessarily the darkness, but the way the paths through spacetime begin to bend toward a single direction. A beam of light, wherever it may be in the universe, always follows the most natural path available to it within reality. In everyday life, that path closely resembles a straight line, so it is easy to imagine light simply racing through space like an arrow. But around an enormous mass compressed into a very small region, space-time itself becomes so curved that the natural path of light no longer matches what intuition expects. Light is not seized by an invisible hand. It simply remains faithful to the shape of reality, and that shape is now tilting deeply toward the black hole. From far away, a ray of light may pass through a region of strong gravity, bend slightly, and then continue its journey among the stars, like a traveler who has briefly changed direction along a winding road. As it moves closer, the curvature grows stronger. Light may circle the black hole before escaping, or settle into delicate orbits around the dark region. The glowing rings seen in simulations and reconstructed images are not the edges of a solid surface. They are the result of light being guided along unusual paths around the boundary of a place that no longer returns signals. Beyond a deeper limit, the paths that once retained some possibility of escaping disappear from the future of light itself, not because light becomes weaker, but because no direction remains within the structure of space-time that leads it back to an outside observer. That boundary is called the event horizon, a name that sounds almost gentler than its meaning. A horizon suggests the place where the sky seems to meet the sea, always visible yet forever beyond reach. An event suggests something that can happen, leave a trace, and be told through some kind of signal. In the physics of black holes, these two ideas meet in a remarkable boundary. Outside it, an event still has a chance to send light or information to the rest of the universe. Inside it, events may continue, matter may follow its own journey, but no ordinary message can cross back through that boundary and return to us. The easiest misunderstanding is to imagine the event horizon as a wall. A wall has a surface, a solidity, something that can reflect sound or leave a sensation against your hand. The event horizon has none of those qualities. If an object were to fall freely through the boundary of a sufficiently large black hole, then according to the classical description of general relativity, it would not necessarily encounter a glowing shell, hear a crack, or experience a dramatic moment announcing that it had crossed the final border. The change lies deeper than direct sensation. Beyond that boundary, every possible path into the future leads farther into the black hole, like a landscape in which every trail, no matter how different it first appears, ultimately slopes toward the same valley with no road back out. A river flowing toward a waterfall offers a gentler way to picture this. While a boat remains far upstream, the current may pull on it, but not strongly enough to make resistance impossible. The rower can still turn around, search for a slower channel, and feel that choice still matters. Closer to the falls, the water never needs to build a wall as a warning. Instead, the current quietly accelerates, gathering every direction into a single flow. Eventually, no matter how the oars are used, the boat is carried toward the drop. The event horizon is much like that point of no return, except that the river is not made of water. It is made of the geometry of space-time. To an observer far away, an object falling into a black hole may appear to slow as it approaches the boundary. The light it emits must climb out of an immensely strong gravitational field. Its wavelength stretches, its color shifts toward the red, its energy weakens, and its signals arrive more and more slowly. The image may gradually fade and redden, seeming to spread thinly across the edge of darkness until it nearly disappears from observation altogether. But this is not the object itself becoming frozen forever. It is the object's final messages being stretched and weakened as they struggle to reach someone standing outside the gravitational well. For the object that is falling, the story does not necessarily look the same. The clock traveling with it continues to measure its own proper time, and if the black hole is large enough that tidal forces at the event horizon are not yet extreme, crossing that boundary may come with no obvious sign at all. There is no glowing doorway, no closing gate echoing through space, no visible line drawn around the darkness. The object simply continues falling. What has changed is not its immediate experience, but the structure of the futures still available to it. Beyond that boundary, every possible path leads deeper into the black hole. This difference between perspectives makes black holes one of the most beautiful places to recognize that the universe does not always tell a single story to every observer. Someone far away sees signals slowing and fading, while the falling object continues along its own passage through time. Neither description contradicts the other. In relativity, space and time are not rigid backdrops that remain identical everywhere. They participate in the story. They curve, stretch, and change shape depending on gravity and motion. The idea may feel unfamiliar, but it is also why a clock near a strong gravitational field does not completely agree with a clock far away, even though both are keeping time correctly within their own circumstances. The event horizon is therefore more like a boundary of communication than the edge of an object. It divides the universe into the part that can still send us messages and the part that has left all ordinary channels of exchange. What lies inside is not necessarily nothingness, nor is it necessarily a dark room with a familiar shape. What seems more certain, according to current descriptions, is that whatever happens, there can no longer send light back out to become part of the sky our telescopes observe. The silence beyond the boundary does not prove that the story has ended. It only tells us that the story is no longer being told through the old route. There are things in life that are known only through traces, never through direct testimony. A dream that fades away may leave behind only a vague feeling upon waking. A passing breeze may be recognized by the curtain it gently moved. Someone crossing a dark room may leave no visible image, yet the floor and surrounding objects still carry subtle signs of their passage. A black hole is recognized in much the same way, only on a far deeper scale. Outside, it still moves stars, heats gas, bends light, and stirs spacetime itself. Inside, it no longer sends signals outward in forms we know how to read. It is this one-way nature that makes the question of a black hole's interior so different from many other astronomical mysteries. If an object is simply too distant, we can hope for larger telescopes to gather more light. If it is hidden by dust, we can observe at different wavelengths. If it is too faint, we can watch longer, more patiently, and allow data to accumulate little by little. But the event horizon is not a technical limitation that can be overcome merely with better instruments. It is a limitation woven into the way causes, signals, and futures are connected through spacetime. No light returns from beyond the boundary. No ordinary message travels back outward. No direct image exists of the deepest interior. Even so, a boundary that cannot be seen through does not force science to stop listening. The region outside still contains much to read carefully. The size of the shadow reveals the mass. The way light bends around it tells us about the shape of nearby spacetime. The motion of hot gas can reveal its spin. Gravitational waves from mergers carry the signatures of the two black holes before they became one. Science becomes like someone standing outside a closed room, unable to hear the conversation within, yet still noticing the faint vibrations beneath the floor, the changing light beneath the door, and the subtle tremors passing through the walls. What matters most is not the image of a magical doorway, but the subtle difference between being unseen and being non-existent. Matter that crosses the event horizon does not instantly vanish into nothingness at the boundary. Light is not extinguished by a solid shell. The story is simply redirected into a region from which outside observers no longer receive the next page. It is the gap between no longer visible and no longer there that opens a remarkably deep space for thought, one that urges physicists to be careful with every conclusion about final endings. Even if we stopped at the event horizon, black holes would already be enough to reshape our intuition about light and time. But the equations of general relativity continue farther. They do not treat that boundary as the place where the falling object comes to rest. Instead, they carry the story deeper, toward a region where density and the curvature of spacetime become extreme. From the outside, the event horizon is where the story can no longer be sent back. Within the physical model, however, it is only the entrance to a more difficult question. If every path leads deeper inward, what exactly is that deepest place? Ahead lies not merely the problem of a curtain that blocks our view, but the problem of time itself and the geometry of reality. Inside a black hole, the things we usually call direction, distance, future, and center no longer arrange themselves according to everyday intuition. To approach the question of whether a black hole might conceal something more than an ending, we must move one layer deeper, into a realm where time no longer resembles the quiet flow we experience in this room tonight. Beyond the event horizon, the hardest thing to imagine is not simply the darkness. Darkness remains a familiar image, no matter how deep it becomes. What is more difficult is that time itself, the thing we usually experience as a steady flow, begins to lose its familiar character. In this quiet room, 1 minute seems much like the next. The clock advances with each tick. Our breathing rises and falls in a gentle rhythm, and the world around us appears to rest upon a stable foundation of time. Near a black hole, however, that stability is no longer something we can take for granted. General relativity does not treat time as a giant clock hanging outside the universe, running identically everywhere. Time is woven together with space into a single structure, one far more flexible than everyday intuition suggests. When matter and energy are present, that structure curves. When an enormous mass is compressed into an extremely small region, the curvature becomes so extreme that the paths of light, the motion of matter, and even the ticking of clocks are affected. A clock far from a black hole and a clock descending into a strong gravitational field no longer agree perfectly, not because one is broken, but because each exists within a different shape of spacetime. Viewed from afar, time near the event horizon appears to slow down. An object falling toward a black hole sends light outward to a distant observer, but that light must climb out of an increasingly deep gravitational well. Each signal arrives later, weaker, and redder, like a sound stretched out, as its source drifts away through a landscape that is no longer ordinary. To someone watching from a distance, the object may seem to fade near the edge of the shadow, as though its time is slowing almost to a halt before it disappears from observation. Yet that image is not the whole story, because time always depends on the path an observer follows. For the object that is falling, its own clock continues to run. If we set aside the tidal forces that can become extreme around smaller black holes, crossing the event horizon of a sufficiently large black hole may not feel like a sharp break in experience. There is no bell announcing that the rules of time have changed. No thin line of light marks the final boundary across space. The object simply continues into its future. What has changed is not its immediate sensation, but the structure of the futures available to it. Beyond that boundary, those futures no longer contain paths leading back out. This is part of what makes black holes both quiet and profound. The greatest transformation does not necessarily arrive as a dramatic event, but through a reordering of every possibility that comes next. It can be helpful to imagine spacetime around a black hole as a landscape that gradually tilts. Far away, many paths remain open. Light can travel sideways, matter can orbit, and signals can still be sent home. The deeper one goes, the more the landscape leans, as though every valley is leading toward the same unavoidable low ground. Beyond the event horizon, the strange thing is not that a new force suddenly appears. It is that moving toward the center begins to resemble moving toward the future. A person cannot choose to stop moving toward tomorrow. In much the same way, an object inside a black hole cannot choose a path that avoids the deeper interior, at least if classical general relativity continues to guide the story. This is why the phrase, "inside a black hole," can be misleading. In everyday life, the inside of an object usually means a room, a core, or a center occupying a place in space, something we might visit, leave, or point to as a location. But inside a black hole, according to general relativity, the center no longer resembles an ordinary destination waiting somewhere ahead in space. It is more like an unavoidable moment in the future of everything that has crossed the event horizon. In other words, moving deeper is not simply traveling to another place. It is also moving towards something that time itself is directing you toward. This image need not feel frightening. It serves more as a distant reminder that human intuition evolved in a much gentler part of the universe. We live on the surface of a planet whose gravity feels comfortably familiar, beneath a sky where sunlight reaches us in a matter of minutes, within an environment where the clock on the table and the heartbeat in our chest seem to share the same sense of time. Because of this, it is easy to think of time as a single river flowing uniformly everywhere. A black hole quietly challenges that assumption, not with an explosion, but with a deeper geometry, one in which that river can bend so profoundly that every branch within it flows toward the same future. From afar, scientists cannot place a clock inside a black hole and receive the results back, but they can test their ideas about time and spacetime through the clues found around its edge. Light bends around massive objects. Stars move around invisible concentrations of mass. Signals emerge from disks of hot gas. And perhaps most strikingly, gravitational waves from black hole mergers reveal that spacetime is not a rigid and motionless stage. When two black holes spiral together, they do not merely move through space. They cause space and time themselves to vibrate, sending faint ripples across the universe. Those ripples arrive on Earth as evidence that the geometry of reality can stretch, oscillate, and carry the memory of tremendously powerful events occurring far away. This understanding does not open a direct door into the interior, but it makes the question of the interior more serious. If space-time can curve, ripple, stretch, and alter the passage of clocks in the outer regions, then in deeper places where curvature becomes extreme, we should not expect ordinary intuition to remain a reliable guide. A question such as, "Where does an object go when it falls into a black hole?" no longer resembles asking where a stone goes after dropping into a well. Instead, it becomes a question about how that object's future is written when spacetime itself has changed the meaning of distance and time. There is a common way of describing the interior of a black hole by saying that space and time somehow switch places. The phrase can be useful if understood carefully as a metaphor for how profoundly intuition is overturned, rather than as a simple magical transformation. Outside a black hole, one can, at least in principle, remain at a fixed distance if enough force is applied. Inside the event horizon, the distance leading deeper inward is no longer something that can be avoided simply by turning around. It becomes unavoidable in much the same way that tomorrow is unavoidable for us. An object may move in many ways through its own proper time, but all of its future paths lie within the deeper regions of the darkness. For that reason, what happens inside a black hole is very different from an ordinary fall. A leaf drifting toward the ground can still be described by positions in space, higher, lower, touching the earth, finally at rest. An object passing through the event horizon enters a picture in which the question, "Where is it?" can no longer be separated from the question, "Where is its future leading?" It is this deep connection between location and time that makes the interior of a black hole so difficult to describe in ordinary language. We still use words such as inside, outside, deeper, and center, but each of those words carries a different weight once it enters the black hole. If we listen carefully, this may be one of the gentlest parts of physics, despite its depth. Time is not a rigid track running through the entire universe. It is more like part of the fabric within which everything lives, and that fabric can sag, stretch, vibrate, or tilt toward a future from which there is no return. Near a black hole, the fabric is no longer flat. Beyond the event horizon, it does more than curve, it rearranges directions themselves, until what we call moving inward becomes inseparable from what a falling object experiences as moving forward in time. This also helps keep the question of another universe from slipping too quickly into pure imagination. If time inside a black hole is already unlike time outside, and if the paths into the future have been bent in ways that outside observers cannot directly witness, then any hypothesis about what lies deeper must begin with that humility. We cannot simply imagine a dark room at the center of a black hole and place another universe inside it like a jewel in a box. A more subtle perspective is required, one in which space-time itself may continue into forms from which the outside can no longer receive signals. The deeper classical general relativity follows its own description, the more relentlessly it guides every path toward a region known as a singularity. But before arriving at that name, which sounds so much like a final period, it is worth holding on to one essential idea. The interior of a black hole is not merely an ordinary darkness. It is a region where future and direction bend into the same story, where time no longer resembles the familiar flow marked by the clock beside your bed, and where physics begins to approach the edge of the very language it uses to describe the universe. If the event horizon is the place where the story can no longer be sent back to the outside world, then the deeper interior is where that story itself becomes difficult to continue using the old concepts. And at the end of the paths drawn by general relativity, a quiet name appears, the singularity, not quite as an answer, but as the first sign that our map is approaching the edge of the page. As we move deeper beyond the event horizon, the story no longer resembles a descent through darkness in any familiar sense. There is no ground waiting below, no bottom of a well, and no central chamber where matter eventually arrives and comes to rest. In the description offered by general relativity, every future path inside a black hole is drawn toward a region that mathematics calls a singularity. Yet that name can easily send the imagination too far, too quickly. It sounds like a place, a tiny point hidden at the center of the darkness. In a deeper sense, however, it is more like a warning issued by the theory itself. The concepts being used have been pushed to the edge of what they can describe. A grain of dust, a fragment of rock, a stream of hot gas, or the collapsed core of a star. Once any of these have crossed the point of no return, the classical picture offers no path that avoids the deeper interior. This is not because a mysterious new force suddenly appears and drags everything toward a tiny point at the center. It arises from the geometry of space-time itself, from the way future-directed paths have been reshaped. Outside a black hole, one can still imagine standing still, turning around, taking a different route, or escaping with enough energy. Inside, those possibilities are no longer arranged in the same way. Every step forward in an object's own time carries it closer to a region where the classical theory can no longer continue the story in an ordinary manner. In mathematical language, a singularity is often associated with quantities becoming infinite. Density no longer means merely an unimaginably large number. It approaches a limit where the number itself ceases to have its usual physical meaning. The curvature of space-time is no longer simply a fabric bent into an extreme depression. It becomes a signal of something reaching an ultimate limit within the equations. When we hear the word infinite, it is easy to imagine something that truly exists with zero size and immeasurable density. But in science, infinity is often not an object we can point to. More often, It resembles the sound of a model beginning to crack when pushed beyond the domain it was built to describe. Imagine a map that works remarkably well. It guides us across fields, through cities, over bridges, and around mountain ranges. For most of the journey, the map is so reliable that we almost forget it is only a representation of the world. But if we continue into a region where the paper begins to blur, where lines overlap, symbols stretch out, and eventually tear apart at the edge, we do not immediately conclude that the real world ends at that tear. A more reasonable conclusion is that the map is no longer sufficient to continue. A singularity inside a black hole should be understood in much the same way, not as a landscape that has been directly seen, but as the place where our current map of physics loses its ability to provide a complete description. General relativity remains one of the most beautiful achievements in science because it describes gravity not as a simple force pulling objects together, but as the shape of spacetime itself. The theory has passed countless tests, from the subtle shift in Mercury's orbit, to the bending of light near the Sun, to the gravitational waves detected from black hole mergers. Its value is not diminished simply because it encounters a limit. It is like a brilliant lamp that illuminates an entire valley with extraordinary clarity. If the path eventually disappears into a canyon that is too narrow and too dark for the light to reach, the fact that the lamp cannot illuminate every corner does not diminish everything it revealed before. For that reason, a singularity should not be told as a simple failure of a theory, but as an important signpost. It tells us that when gravity becomes too strong, when matter is compressed to extraordinary densities, and when space and time are drawn together in ways that exceed intuition, a deeper layer of physics may be required. General relativity is exceptionally good at describing the very large. Planets, stars, galaxies, black holes, and the expansion of the universe. Quantum mechanics is exceptionally good at describing the very small. Atoms, particles, quantum fields, and fluctuations on scales the human eye could never perceive. But inside a black hole, the very large and the very small meet in the same place. An immense mass is compressed into an extreme region, and there, the two great languages of modern physics have not yet merged into a single, complete voice. That incompleteness is precisely what gives the singularity its special pull. It is not merely a detail hidden inside a dark object. It is the place where physics is forced to look directly into the gap between its two most successful theories. If we rely only on general relativity, the story leads toward an extreme limit. If we rely only on quantum intuition, gravity in such a powerful regime cannot be described so simply. Scientists have explored many possible paths across that gap, from loop quantum gravity and string theory to semi-classical models and ideas about deeper structures underlying spacetime itself. None of these paths has yet become the final answer, but all of them are driven by the same feeling. Where the equations produce infinities, nature may be asking for a different way of understanding. This perspective also softens the image of a black hole. If we imagine the singularity as an absolute cosmic grinder at the center, the story can feel heavy, almost hopeless. But if we see it as the edge of the map, as a place where our current language is no longer flexible enough to continue, then the black hole becomes less a symbol of destruction and more a doorway into questions. According to our present understanding, anything that falls beyond the event horizon no longer sends signals back out. That is a strict limitation, yet that limitation does not force us to conclude that physics itself ends in an absolute sense. It simply reminds us that the next part of the story cannot be written with the old tools without running into contradictions. There is a particular kind of quietness in that idea. The universe does not need to hide its secrets behind a brilliant wall of light. Sometimes it simply allows the equations to reach a place where they can no longer speak in their familiar voice. It is like a very slow piece of music descending toward notes too low for the ear to hear clearly. The vibrations are still there, just beyond the range of direct perception. A singularity is similar. It is not an image to be seen, but a sign that the story has entered a region where intuition and ordinary language may need to change. Throughout the history of science, the places where theories struggled have often become the seeds of new understanding. Before relativity, small discrepancies in planetary motion and the behavior of light hinted that the older view of gravity was incomplete. Before quantum mechanics emerged, the behavior of light and atoms created questions that classical physics could not answer. Each time, nature did not shout that humanity was entirely wrong. It whispered through tiny deviations, subtle mismatches, and regions where the old formulas remained successful in most situations, but no longer worked at the deepest edges. The singularity inside a black hole may belong to that same kind of whisper, only on a far more extreme scale. From this perspective, the question, is the singularity real, must be asked carefully. It is possible that a complete theory of quantum gravity will eventually reveal that the singularity is replaced by something else, a state of extraordinary but finite density, a transitional region, or perhaps something for which we do not yet have simple words. It is also possible that familiar concepts such as space, time, inside, center, before, and after will need to be rewritten as we approach that region. What seems more certain is that physicists do not treat the appearance of infinity in an equation as an ordinary description of an ordinary object. It is a signal that our current understanding has reached a boundary. That boundary connects black holes to an even larger mystery. When scientists trace the universe back toward its earliest past, classical cosmology also leads toward an extremely hot and dense state, where the idea of a simple beginning becomes difficult to grasp. The Big Bang, like a black hole, should not be viewed through the overly simple image of a tiny point exploding into pre-existing emptiness. It belongs to the history of space, time, matter, and light themselves. Yet the appearance of an extreme region at both ends of the story on one side, collapse inside a black hole, and on the other, the very early universe makes it difficult not to notice a faint resonance between them. That resonance does not mean that black holes and the Big Bang are the same thing. One belongs to a region hidden behind an event horizon within the present universe. The other belongs to the earliest history of the entire observable cosmos. They differ in structure, in role, and in the way they are described. Yet both lead to questions about what happens when general relativity is pushed to its limits, and both point toward the need for a deeper theory in which gravity and quantum physics no longer stand apart. It is precisely at that intersection that more daring ideas, cosmic bounces, singularity avoidance, and the possibility that new regions of spacetime might emerge, begin to find room to be heard. The singularity, then, is not the ending of this story, nor is it the answer to the mystery of black holes. It is more like a pause in the music, a moment where the old melody rests long enough for a new theme to begin. There is still a great deal of uncertainty ahead, and that uncertainty deserves to remain intact. But if there is one place in this story that changes how we see black holes, it is here. The deepest region matters not simply because it is extreme, but because it reveals that science has not yet found its final map of reality. Seen this way, a black hole is no longer a simple tunnel leading toward a predetermined answer. It becomes a place where questions about endings, beginnings, time, and spacetime begin to touch one another. Outside, we see darkness and a boundary. Inside the model, we see paths leading toward an extreme limit. Yet at that limit, rather than hearing a door slam shut, modern physics hears an empty space waiting to be understood more deeply. And that empty space naturally guides us toward another mystery, one even older than the black hole itself. The Big Bang, where the question of singularities no longer lies within the heart of a black hole, but at the farthest edge of the history of time. When the singularity inside a black hole is viewed as the place where our current map of physics begins to lose its sharpness, another boundary comes into view from the farthest reaches of cosmic history. This boundary does not lie inside a collapsed star, nor is it hidden behind the event horizon of any black hole a telescope can observe. It belongs to the earliest past of the observable universe itself, when galaxies, clouds of gas, stars, and planets had not yet taken on the familiar forms we know today. The name usually given to that era is the Big Bang, though the name itself can sometimes lead the imagination farther than the science. The Big Bang was not a fireball exploding into an already empty space, nor was it an explosion with a central point from which matter scattered outward, like fireworks in the night sky. To picture it that way is to place the young universe inside a larger room, as though space already existed outside, waiting for the explosion to occur within it. In modern cosmology, the more careful picture is this. The observable universe once existed in a state that was far hotter and denser than it is today, and space itself expanded, causing distances between regions to grow over time. The traces of that expansion are not merely abstract ideas. When light from distant galaxies reaches Earth, its wavelength is often stretched toward the red end of the spectrum, showing that space expanded during its journey. The farther we look, the farther back in time we see, because light requires immense spans of time to reach us. The most distant galaxies are not only remote in space, they are also ancient images of the universe, sent to us when the cosmos was far younger than it is now. This redshift is one of the key observational foundations that revealed a universe that is not static, but one that has evolved and continues to evolve on the largest scales. Another trace is even gentler, yet perhaps deeper: the cosmic microwave background. It is not as brilliant as starlight, nor as visually dramatic as a nebula or a galaxy, but it fills the sky like a faint warmth left behind from the universe's youth. When the cosmos cooled enough for light to travel freely, those ancient photons began their long journey. Over billions of years of expansion, their wavelengths stretched into the microwave range, and today they remain as a cold, nearly uniform background signal, carrying memories of an era before the first stars were ever lit. Together with the observed abundance of light elements such as hydrogen, helium, and a tiny amount of lithium, these traces make the Big Bang model far more than a speculative story. It is a scientific framework built upon multiple lines of evidence. The universe was once hotter and denser than it is now. The universe expanded. The universe cooled. Once it cooled enough, light could separate from matter and move freely through space. Later, in regions that were only slightly denser than average, gravity gradually gathered matter together, eventually forming stars, galaxies, and the vast cosmic web that modern telescopes now observe. This picture is robust enough to serve as the foundation of modern cosmology. But that does not mean science has reconstructed every moment of the beginning. As models are traced back toward earlier and earlier times, temperatures rise, densities increase, characteristic distances shrink, and physical conditions become increasingly unfamiliar. At a sufficiently early stage, classical general relativity once again approaches an extreme regime where certain quantities can become infinite within the mathematical model. Just as with the singularity inside a black hole, this is generally taken as a sign that the theory has reached its limits, not as a direct photograph of a literal first moment that has been observed. What matters here is the distinction between what is known with considerable confidence and what remains open. The evidence for a hot, dense, expanding universe in the past is extremely strong, but the absolute first instant, if such a phrase is even meaningful, has not been directly observed. The cosmic microwave background does not come from time zero. It comes from a much later era, when the universe had cooled enough for light to decouple from the hot plasma and travel freely. Before that period, our understanding relies on models, calculations, particle physics, and indirect clues, rather than a direct image of the beginning itself. That caution does not make the Big Bang less fascinating. It makes it deeper. If the Big Bang is told simply as an explosion, the questions quickly become overly simplistic. Where did it explode? What was outside it? What existed beforehand? But if the Big Bang is understood as the expansion of space itself from a very early state, those questions must be asked more gently. Space is not a box containing the explosion. It is part of the process. Time is not a clock hanging outside the universe, recording the opening scene. If we travel far enough backward, even the concept of before may require a deeper theory before it can be clearly defined. Compared with a black hole, the Big Bang occupies a very different role. A black hole is a region of extreme gravity that forms within the present universe after matter collapses or after black holes merge. The Big Bang is a model describing the hot, dense, early state of the entire observable universe. One is hidden behind an event horizon. The other is hidden behind the limits of looking backward through time and by the extreme physical conditions of the early cosmos. These should not be merged into a single simple picture, nor should we casually claim that the Big Bang was merely a black hole in reverse. The more meaningful similarity is that both bring our current theories to regions where they remain unfinished. Inside a black hole, general relativity describes the exterior extremely well and predicts the existence of the event horizon, yet deeper inside it leads to a singularity within the classical model. In cosmology, the same theory successfully describes the expansion of the universe across vast stretches of its history, but when pushed back toward the earliest moments, it approaches a similar limit. Both cases remind us that strong gravity, enormous density, and extremely small scales are places where humanity still lacks a complete theory that fully unites general relativity with quantum mechanics. It may help to picture these as two regions of mist at opposite ends of a long road. At one end, a black hole hides its deepest interior behind the event horizon, leaving us clues through stellar orbits, bent light, hot gas, and gravitational waves. At the other end, the early universe leaves behind the cosmic microwave background, cosmic expansion, the abundance of light elements, and the large-scale structure of the cosmos. The two regions of mist are not the same, but both suggest that the light of our present understanding has not yet reached every deepest layer. For that reason, new models of the earliest universe do not arise from a desire to tell unusual stories. They arise from a genuine need within physics. Some approaches attempt to avoid singularities by incorporating quantum effects into gravity. Others ask whether the universe may have passed through an earlier phase before the hot, dense state we call the Big Bang. Still, others explore the possibility that the Big Bang was not an absolute beginning, but simply the earliest boundary to which current models can reliably trace the cosmic story. These ideas differ greatly from one another, and none has become the final answer. Yet they all begin from the same principle. Infinities in equations are often places where science must become more careful, not places where imagination is free to replace evidence. In the quiet rhythm of this story, the Big Bang does not need to appear as an explosion that shatters the darkness. It can instead appear as a hot, dense past of space itself, a state so distant that everyday images can only guide us closer, never replace the science. From that state, the universe expanded and cooled. Ancient light drifted across the sky. Matter gathered into the first stars. Heavy elements were forged in stellar interiors and in violent cosmic events. Eventually, there were planets, oceans, living things, and quiet nights in which human beings could wonder why time seems to possess such a deep past. Seen in this more careful way, the question of black holes also becomes firmer. There is no need to rush toward the claim that a black hole creates another universe. There is no need to turn every dark region into a doorway. It is enough to recognize that both black holes and the early universe confront physics with the same kind of challenge. What happens when space-time is compressed or traced backward into a regime where classical theory is no longer sufficient? From that point, ideas such as cosmic bounces or singularity avoidance gain a reason to exist, not as exaggerations, but as cautious attempts to move beyond the limits of older models. The story has not yet entered a baby universe, nor does it require a dramatic conclusion. It is simply laying the foundation for a deeper possibility. If nature never truly reaches infinity, if singularities are signs of incomplete understanding, then where the old model appears to end, a new description may begin. And in some lines of research, that new description carries the quiet image of a bounce. After following the story of the Big Bang, the most important thing to keep is not a dramatic image of universes instantly emerging from the darkness, but something more modest. In both black holes and the early universe, classical models lead science toward extreme regimes where infinities appear as signs that deserve careful attention. An infinity in an equation is not necessarily a real object waiting at the end of the road. It may simply be the way a highly successful theory tells us that it is being pushed beyond the region where it can provide a complete description. Inside a black hole, general relativity guides every future path beyond the event horizon toward a singularity. In cosmology, when the expansion of the universe is traced backward toward extremely early times, the same theory encounters conditions so hot and dense that the classical model can no longer confidently describe what the very first moment truly was. These two situations are not the same, and they should not be merged into a single simplified story. Yet they raise a similar question: does nature truly allow density and curvature to become infinite? Or does a deeper layer of physics intervene before that point and redirect the course of the story? From that question, the idea of a bounce emerges not as a fantastical spectacle, but as a mathematical possibility within certain lines of research. A bounce is not something that could be watched directly, nor is it like a ball striking the floor and rebounding through ordinary space. It is a gentle way of describing a hypothetical process. Collapse does not continue all the way to an infinite point, but instead encounters a new physical mechanism that shifts the evolution into a different phase. Depending on the model, that mechanism may arise from quantum effects of gravity, from a deeper structure of spacetime, or from physical conditions that classical general relativity does not fully include. This may sound unfamiliar, but throughout the history of physics, it has not been unusual for older theories to require modification in extreme regimes. Newtonian physics remains excellent for describing falling apples, planetary motion, and countless everyday phenomena, yet it must give way to relativity when velocities become enormous or gravity becomes very strong. Classical physics successfully describes many familiar objects, but it cannot fully explain the behavior of atoms and light at very small scales, where quantum mechanics becomes necessary. When black holes bring immense masses and extraordinarily tiny distances together in the same region, expecting a new layer of description is not an exaggeration. It is simply a careful way of continuing the question. Some models within loop quantum gravity suggest that when density approaches the Planck scale, where quantum effects of geometry itself may become important, collapse does not necessarily end in an infinite singularity. Instead, spacetime may pass through a deeply transitional region where the classical description no longer applies. Ideas such as the Planck star have been proposed within this context, suggesting that the interior of a black hole could reach extraordinarily high densities before evolving into a different phase. These remain theoretical ideas, still debated and lacking direct observational evidence, but they demonstrate that the classical singularity is not the only possibility being explored by physicists. Other approaches also attempt to avoid singularities through different mechanisms. Some models examine how spacetime changes when quantum effects or Hawking radiation are taken into account. Others investigate solutions known as regular black holes, theoretical black holes that do not contain a central singularity in the classical sense. Some introduce special conditions such as electric charge, effective pressure, or high-energy corrections that prevent curvature from becoming infinite. These models are not the same, and none should be presented as a final answer. What matters is that modern physics is not compelled to treat the classical singularity as nature's finished picture. For that reason, the idea of a bounce must be held lightly. It is not an event that has been observed inside a black hole, nor is it a promise that every black hole opens into another realm. It is simply one of the ways physicists attempt to imagine what might replace a singularity if a deeper theory keeps physical quantities finite. If the singularity marks the torn edge of an old map, then a bounce is one of the first tentative lines drawn on a new one, a suggestion that the road may not end at the tear, but instead continue through a region that has not yet been directly surveyed. A more familiar analogy can be found in the life of a star before it becomes a black hole. Throughout a star's existence, gravity constantly tries to pull matter inward, while various forms of pressure resist the collapse. An ordinary star is supported by gas pressure and radiation from nuclear fusion. A white dwarf is supported by electron degeneracy pressure. A neutron star is supported by quantum effects and nuclear forces within extremely dense matter. At each deeper level, nature reveals ways for matter to behave that everyday intuition would never predict. A black hole forms when the known mechanisms are no longer sufficient to stop collapse, but that alone does not prove that no other mechanism could emerge at still deeper scales. The difference lies in the level of certainty. White dwarfs and neutron stars are observed objects. They have measurable masses, detectable radiation, known orbits, and abundant data. A bounce inside a black hole, by contrast, remains within a region that has never been directly seen. The idea is motivated by the need to avoid infinities and to unite gravity with quantum physics, but no telescope has yet confirmed that such a process actually occurs in nature. It is important to preserve that distinction, because the clear separation between what is known and what is still being tested is what gives this question its scientific weight. Even if a bounce does occur in some model, an outside observer might never witness it directly. The event horizon prevents ordinary light and signals from returning, while the extreme time dilation near a black hole makes internal processes appear very different when compared with clocks far away. A process may unfold according to the proper time of whatever is falling inward, yet from the perspective of the outside universe, any trace of that process could be stretched, hidden, or revealed only through extremely indirect effects. This is what makes bounce models both fascinating and difficult to test, and why they must always be discussed with caution. Nature may have a way to avoid singularities without creating any kind of baby universe at all. Perhaps the interior of a black hole is only a deep, sealed quantum structure, one that leaves behind no image that ordinary language can easily hold. Perhaps today's models are still only experiments, like the first sketches made before a complete theory of quantum gravity finally appears. These possibilities do not make the subject less fascinating. On the contrary, they make it more credible, because the universe is not forced to behave according to the image human beings find most appealing. Science follows only the models that can be calculated, compared, and, if we are fortunate, tied to predictions that can be tested. In recent years, theoretical research has continued to explore many ways of describing black holes without requiring a central singularity in the classical sense. Some studies examine the role of Hawking radiation, electric charge, quantum structure, or geometric corrections in extreme regions. These proposals do not agree on a single unified picture, but they reflect a shared point in modern physics. The singularity is not a detail that everyone is comfortable treating as the true ending of nature. It is a problem to be solved, a place where theories must be tested, and perhaps a place where a new principle is waiting to be recognized. If we listen slowly, the idea of a bounce does not need to feel dramatic. It can be understood as a very deep shift in the language of physics. A collapse continues until the old model is no longer sufficient, and then, instead of allowing the numbers to run toward infinity, a new description keeps the story finite. What happens after that depends on the specific model. Some models produce only a more regular core. Some suggest a remnant state. Some try to connect the process with a white hole. Others go farther and ask whether a new branch of spacetime could form. But here, the essential point remains the first foundation. A bounce is a theoretical possibility for avoiding a singularity, not evidence for another universe. That caution keeps the subject from drifting away from science. An observed black hole is still a region with an event horizon, mass, spin, and gravitational influence on its surroundings. Images of black hole shadows, stellar orbits, and gravitational waves do not directly reveal a bounce inside. They confirm that black holes exist and that general relativity describes the exterior region extremely well. The interior remains a place where deeper models must compete. In other words, what is certain is that black holes are real. What remains uncertain is what, if anything, replaces the singularity. If the singularity is truly replaced. From this point, the path of the question becomes clearer, but it does not need to widen too quickly. If the singularity is a sign of an incomplete theory, and if some models allow collapse to transition into a more finite state, then a black hole no longer has to be imagined as an absolute period at the end of every physical possibility. It is still a place from which light does not return. It is still a place where outside observers do not receive the story directly. But in the region those observers cannot see, new equations may be trying to write a different ending for collapse. Only once that foundation is clear can the idea of a baby universe appear without weakening the credibility of the story. A baby universe, when mentioned in science, should not appear as an imaginary world already placed inside the darkness. It should be treated as one of the more distant consequences of certain models that attempt to avoid singularities and extend the geometry of spacetime. It is a speculative possibility, not a scene that has been observed. But after we understand why physics wants to avoid infinities, why a bounce is considered, and why the event horizon makes direct testing so difficult, the question begins to stand on more serious ground. Inside a black hole, if nature truly does not end in an infinite singularity, what lies beyond that point could differ greatly depending on which theory is correct. It may be only a deep quantum core. It may be a kind of remnant. It may be a transitional process for which we do not yet have language that is easy to imagine. And in some more daring models, it may be a new branch of spacetime, separated from the parent universe by the very boundary that prevents signals from returning. From here, the question of a baby universe is no longer a sudden leap of imagination, but the next layer of a physical problem that began with the singularity itself. In the deepest part of this story, the phrase baby universe can easily carry the imagination farther than the science. It sounds like a small world already waiting inside the darkness, as though crossing a black hole would simply lead into another sky. But in physics, that picture is far too simple. A baby universe, if it appears in a model at all, is not a room hidden behind a door, nor a sphere neatly contained within a black hole. It is closer to the idea of a branch of space-time, a structure that may become so disconnected from its original region that observers outside can no longer receive direct signals from it. That description is less colorful than the images often found in science fiction, but it is far more important. It keeps the question grounded in physics rather than drifting into mysticism. Real black holes possess event horizons. Outside those boundaries, we can measure shadows, stellar orbits, hot gas, and gravitational waves. Beyond them, light does not return, which means any model of the deeper interior must proceed through mathematics, physical principles, and indirect clues, if such clues exist at all. The more daring an idea becomes, the more slowly it must be told, because the distance between possible within a model and known to occur in the real universe is a very large one. The concept of a baby universe appears in several different areas of theoretical physics. Sometimes it arises in discussions of quantum gravity, where spacetime on the smallest scales may no longer resemble the smooth picture provided by classical theory. Sometimes it appears in questions about singularities and how an extreme region might continue if physical quantities never truly become infinite. In other cases, it enters broader cosmological hypotheses in which black holes are considered possible origins of new spacetime domains. These uses are not identical, and for that reason alone, the phrase baby universe should always be approached with caution. One of the best-known examples is the idea of cosmological natural selection proposed by physicist, content reference, OASITE, 0, index equals 0. In that picture, black holes may be connected to the birth of descendant universes, and the physical constants in each universe may vary slightly from one generation to the next. If a universe possesses conditions that produce more black holes, it may also produce more descendants within that framework. It is a bold idea, but it remains a hypothesis. It has not been confirmed by observation, nor does it represent a broad consensus within modern physics. Its value lies in attempting to turn the question of black holes into a structured scientific problem rather than leaving it as a vague image of darkness. Other approaches do not go so far as to speak of universes reproducing themselves. In some quantum gravity models, the classical singularity may be replaced by a region with a different internal structure, where space-time does not end in the usual mathematical sense. If a new branch is permitted by the model, it does not necessarily resemble our universe with galaxies, stars, and planets. It may be only a feature of the mathematical structure, a possibility within the continuation of space-time, or a region causally disconnected from the exterior. This description is less exciting than an interstellar adventure story, but it is much closer to the way science actually works. Cautiously, with clear limits, and always open to the possibility of being wrong. The appeal of these ideas does not come from providing an easy answer. It comes from appearing precisely where our current theories encounter difficulties. General relativity describes the exterior of a black hole extraordinarily well, from the bending of light to the production of gravitational waves during mergers. Quantum mechanics reminds us that information and physical states should not simply vanish without explanation. Black hole thermodynamics tells us that black holes possess entropy, temperature, and, in semi-classical descriptions, Hawking radiation. These pieces do not automatically lead to baby universes, but they do make the interior of a black hole a place where physics is not satisfied with overly simple answers. Alongside the fascination lies a very hard limitation that cannot be ignored. If a new branch of spacetime truly forms beyond an event horizon, it may send no messages back to the parent universe at all. No light returns. No instrument can enter and report its findings. No telescope can record a direct image. This makes baby universe hypotheses extremely difficult to test. A successful model must somehow produce consequences that can be observed from the outside, or at the very least remain consistent with what is already known about black holes, the Big Bang, Hawking radiation, gravitational waves, and the structure of the cosmos. Without some possibility of testing, even the most beautiful idea remains far from the most secure territory of science. Making that distinction helps the question become calmer. Black holes are real. Their shadows have been reconstructed from observational data. Gravitational waves from black hole mergers have been measured. The Big Bang rests on strong observational foundations, including cosmic expansion, the cosmic microwave background, and the abundance of light elements. Baby universes, by contrast, remain in the realm of hypothesis, where models attempt to extend the story beyond the point where singularities once appeared. When these three layers are placed in their proper positions, the subject no longer resembles a wild tale. It becomes a journey along the boundary between what is known, what models permit, and what remains untested. Within that boundary, language must move slowly. The phrase, hiding another universe, should not be understood as a black hole already containing a fully formed world waiting to be discovered. It is better understood as a question. Could extreme gravitational collapse lead to a continuation of spacetime, from which outside observers can no longer receive signals? The question preserves the strangeness of the subject without forcing science to claim more than it knows. It allows curiosity and caution to exist side by side. One reason baby universes are difficult to discuss is that they offer no direct observational image. For neutron stars, we can measure radio pulses, X-rays, masses, and orbital motions. For black holes, we can observe gravitational effects, accretion disks, shadows, and gravitational waves. For the early universe, we have the cosmic microwave background, redshift, and the signatures of light elements. But if a baby universe is causally disconnected from its parent universe, observation nearly slips from our grasp. What remains are models, internal logical consistency, connections to problems such as singularities and information, and the hope that some indirect effect may eventually distinguish one model from another. For that reason, there is no need to make the idea louder than it already is. It is deep enough in its own quietness. Out there, a dark region confirmed by data may contain a question that no telescope has ever directly seen. Classical equations lead the story towards singularities. New models attempt to avoid those singularities in different ways. In some of those attempts, a new branch of spacetime is theoretically allowed. At that point alone, the question is already large enough without any exaggeration. If one day the idea of baby universes is replaced by a better model, it will still have served an important purpose. It will have forced us to think more carefully about what we mean by inside, beginning, ending, and space-time. If some part of the idea survives into future physics, black holes may become an even deeper link in the story of cosmic origins. Either outcome preserves the beauty of the present moment. The beauty lies not in having the answer, but in asking the question carefully enough not to injure the truth. Behind the concept of a baby universe lies a question that feels closer to us. If a new branch of spacetime can emerge in certain black hole models, should we wonder whether our own universe might have originated through a similar process? It is an alluring question, but also one that can easily be told incorrectly if we move too quickly. It must rest on firmer ground. Our universe has a hot, dense past. It is expanding. It carries observable traces of its history, and there remains a very early era through which current models cannot yet see completely. Only from that foundation does the possibility that we might inhabit the other side of some deeper process begin to acquire scientific meaning. Right now, in the quiet space surrounding Earth, a very ancient layer of light is still passing through. It does not brighten the room. It does not appear as a streak across the sky. It carries none of the brilliance of distant stars. It has traveled through nearly the entire history of the universe, stretched by the expansion of space, cooled over billions of years, and become a faint microwave signal spread across every direction. This is the cosmic microwave background, one of the clearest traces that the universe was once far hotter, denser, and younger than it is today. That light does not come from the absolute first moment. It was released after the universe had existed long enough to cool, allowing electrons to combine with atomic nuclei and form the first neutral atoms. Before that time, light was constantly scattered within a dense, hot sea of plasma and could not travel freely to create a clear image. Afterward, photons began their long journey through space, and as the universe expanded, their wavelengths stretched into the cool microwave range. In that sense, the cosmic microwave background is like a fog of ancient light. It does not reveal the very first day of everything, but it preserves a remarkably early portrait of the universe before stars and galaxies had yet appeared. Together with the redshift of distant galaxies and the observed abundance of light elements, this ancient light places the Big Bang model on a strong observational foundation. The observable universe once existed in a hotter and denser state. Space expanded, temperatures gradually fell, matter transitioned from plasma into atoms. Gravity then slowly gathered slightly denser regions into larger structures. The first stars appeared, followed by galaxies, galaxy clusters, and the vast cosmic web. Much later came rocky planets stable enough to hold oceans, atmospheres, and eventually life itself. This picture does not need a bold hypothesis to be fascinating. It is already profound in its own truth. The simple fact that the sky still carries a faint glow from a time when the universe was not yet transparent makes the history of space feel remarkably close. That light comes from every direction. It does not point toward a special center. It does not tell the story of an explosion with a single origin point. Instead, it quietly reveals that the entire observable universe passed through a common hot and dense phase. When instruments map the tiny fluctuations embedded within that ancient glow, they are doing more than capturing an old photograph. They are reading the earliest seeds of cosmic structure. Yet even the oldest light we can observe is not the first page of the book. It is more like an early page that still carries fresh ink, appearing after an opening chapter that light itself cannot directly deliver to us. The era before the cosmic microwave background must be reconstructed through particle physics, cosmological models, and indirect clues hidden in large-scale structure and in the subtle patterns imprinted on the microwave sky. The farther we move toward those earliest moments, the more our descriptions depend on aspects of nature that remain only partially understood, especially the way gravity and quantum mechanics operate together when density and energy become extraordinarily large. In those very early regions, science is no longer merely reconstructing the history of stars and galaxies. It begins to touch the deeper foundation of spacetime itself. General relativity describes cosmic expansion with remarkable success across many scales, but when pushed far enough backward, the classical model approaches extreme conditions. Quantum mechanics, which is essential on the smallest scales, has not yet been fully united with gravity in a thoroughly tested theory. That incompleteness does not undermine the Big Bang picture. It simply places a thin veil over the earliest chapter, where familiar ideas of space and time may need to be rewritten more carefully. Alongside black holes, the earliest universe creates a quiet parallel. A black hole hides its deepest interior behind an event horizon. The early universe hides the era before the cosmic microwave background behind a hot, dense phase through which light could not yet travel freely. These two forms of concealment are fundamentally different, yet both force us to read the universe through traces rather than direct observation. One leaves behind shadows, stellar motions, hot accretion flows, and gravitational waves. The other leaves behind microwave radiation, redshift, light element abundances, and tiny fluctuations that later grew into galaxies. It is this parallel that has led some theoretical models to place black holes and cosmic origins closer together in thought, though not in proof. In such models, the hot, dense state of an expanding universe may be described as the continuation of some deeper extreme process. A collapse that does not end in an infinite singularity might, in certain mathematical formulations, transition into a new phase of spacetime expansion. This remains a realm of controlled speculation rather than a conclusion of standard cosmology, and current observations do not require science to accept such a picture. An honest account must keep each layer of understanding in its proper place. The hot, dense early universe is supported by strong evidence. Black holes and event horizons are supported by compelling observations and reconstructed images of their shadows. Singularities arise as signals within classical models push to their limits. The possibility that a universe could emerge from a process related to a black hole remains a matter of active hypothesis and debate. When these layers are carefully separated, the larger idea no longer feels exaggerated. It becomes a distant frontier of physics, where questions are preserved without being forced into answers. To say that we are living inside a black hole is therefore easy to misunderstand. It encourages images of the sky as the inner surface of a giant dark sphere, or the idea that an ordinary outside space exists somewhere beyond the universe. A more careful scientific interpretation does not rely on such pictures. In models that connect black holes to new universes, any separation is usually one of causality and space-time geometry, not a material shell surrounding us that could be pointed to. Words such as inside, outside, parent, and child are borrowed metaphors, helping intuition approach mathematical structures that are otherwise difficult to visualize. This perspective keeps the discussion closer to evidence and farther from fantasy. There is no need to imagine that every black hole already contains stars, galaxies, and other skies waiting within. There is no need to turn the origin of the universe into a cinematic scene. It is enough to recognize that science encounters two frontiers: the inner frontier of a black hole, where signals do not return, and the earliest frontier of the observable universe, where even the oldest light does not reach the very beginning. Between those two frontiers, physicists explore different mathematical languages in an effort to describe what happens when spacetime enters its most extreme regimes. In the quiet rhythm of this story, the cosmic microwave background serves as a gentler reminder than any sensational image could provide. It does not tell us that every mystery has been solved, nor does it hide the entire history of the universe behind darkness. It rests between those extremes, a very ancient light that tells us the universe was once younger, hotter, and denser, while still leaving behind a region we have never seen directly. From that unseen region emerge ideas about cosmic inflation, singularity avoidance, transitional phases, and deeper continuations of spacetime, each attempting to move one step farther. The possibility that our universe might somehow be connected to a black hole, therefore, does not need to stand at the center of the story as a declaration. It passes through the narrative as a distant possibility, arising when extreme regions of physics are considered side by side. What remains more certain, and perhaps more beautiful, is the humility that data teaches us. There are places where light has told us much, such as the cosmic microwave background. There are places where light stops telling its story, such as beyond an event horizon. There are regions where models speak with confidence, and others where they have only begun to take their first steps. The universe does not become less wondrous when those boundaries are acknowledged. It becomes more trustworthy and deeper. One day, more sensitive measurements of primordial gravitational waves, large-scale cosmic structure, the microwave background, or black hole physics may help distinguish among some of today's competing models. Some bold ideas may gradually fade. Others may survive because they agree more closely with the evidence. Science often moves this way not through a sudden leap into certainty, but by allowing models to stand beneath the light of observation for long enough. Meanwhile, the sky continues to carry its ancient microwave glow. Black holes continue to hold their silent shadows from which no signals return. Between those two different silences, the question of a larger story remains not loud and not burdensome. It does not require us to believe that our universe was born from a black hole. It simply opens the possibility that the origin of spacetime may be deeper than the first picture we learned, and that what we call a beginning may sometimes be only the earliest boundary that light and our current models are still capable of describing. From that ancient past, the story now returns to black holes in a way that is closer to observation and testability. When an object falls through an event horizon, it carries more than mass. It carries states, structure, physical history, and information that quantum mechanics does not easily allow to disappear completely. The interior may never send light back out, but the question of information remains outside, lingering far more persistently than our first intuitions might suggest. A black hole can leave many traces in the universe, while still keeping its deepest interior hidden. The hot gas near its edge can shine with extreme intensity. Nearby stars can be pulled into very rapid orbits. Light from distant backgrounds can be bent around its shadow. When two black holes merge, spacetime itself can ripple and send gravitational waves across vast cosmic distances. All of these signals allow us to know that black holes are real, that they have mass, rotation, and a history of interaction with their environment. Yet they all remain confined to the outside region, where the universe still allows information to travel back toward an observer. This limitation makes any hypothesis about the interior far more difficult to test than most other questions in astronomy. A distant planet can be studied through the light of its host star, through its orbit, or through the tiny dimming it causes as it passes in front of the star. A neutron star can reveal itself through radio pulses, X-rays, bursts, or gravitational waves during collisions. Even a very distant galaxy still sends ancient light to our telescopes, however faint and redshifted it becomes over time. But the region beyond a black hole's event horizon does not return light, does not send a direct record, and does not allow an instrument to enter and come back with an answer. This difficulty is not simply a matter of lacking a powerful enough telescope. A stronger telescope can see farther, resolve finer details, and collect more photons from faint objects. Better detectors can pick up weaker ripples in spacetime. But the event horizon is not a cloud that can be seen through with a different wavelength, nor a darkness that can be overcome with longer exposure times. It is a boundary in the causal structure of spacetime itself, where signals from the inside no longer have a physical path back to the outside universe. An image of a sealed room can help soften the intuition, but it must remain limited. In an ordinary room, an observer outside can still hope to hear sounds, see light through a crack, or eventually open the door. A black hole is far more strict. The exterior may still vibrate, shine, and carry traces of matter before it crosses the final boundary. Beyond that boundary, familiar modes of communication simply cease to function. The door does not merely close. The very route by which sound and light could return no longer lies within the future of what falls in. For this reason, hypotheses about baby universes or new spacetime branches cannot be tested by direct observation. A model that replaces the singularity with a bounce must be validated in other ways. It must remain consistent with well-tested laws. It must preserve the major successes of general relativity in the exterior region. It must be compatible with quantum mechanics, black hole thermodynamics, and increasingly precise observational data. If possible, it should produce indirect signatures, subtle differences in gravitational waves, radiation, black hole evaporation, or imprints from extreme conditions in the early universe. If such signatures exist at all, they are extremely difficult to separate from the background noise of the universe. The gravitational waves from a black hole merger are already extraordinarily faint by the time they reach Earth, even though the original event releases enormous energy. The tiny differences between a classical black hole and a quantum-corrected object without a singularity, or between competing quantum models of the interior, may lie in the very late stages of the signal, in hypothetical post-merger echoes, or in features that current instruments are not yet sensitive enough to confirm. Scientists can search, compare, and gradually rule out possibilities, but the distance from a weak hint to a solid conclusion remains very large. Here, the patience of science becomes part of the story itself. A hypothesis that is difficult to test is not automatically meaningless, but the further it lies from direct observation, the more rigor it must endure. It cannot rely on elegance alone, or on how striking its picture appears. It must have clear mathematical structure, well-defined predictions in specific regimes, and reasons for improving upon existing theories. It must then survive comparison with data. Some ideas that once seemed speculative have been narrowed or reshaped by new data. Others, initially unfamiliar or even strange, have gradually become foundations of modern physics as subtle evidence accumulated over decades. Black holes themselves once lived at the edge of what seemed plausible in equations, long before stellar motion, X-rays, shadow images, and gravitational waves turned them into observed realities. Gravitational waves were once a delicate prediction of general relativity, long before they became measurable signals in detectors on Earth. This history does not prove that baby universes are real, but it does remind us that physics often requires long intervals before an idea can move from equations into data. The difference lies in predictability. Black holes and gravitational waves produce clear, testable signatures, shadow sizes tied to mass, stellar orbits around galactic centers, waveforms determined by mass and spin. For baby universes, the problem is far more severe. A new spacetime branch, if truly causally disconnected, may leave no direct message in the parent universe at all. Any test must therefore rely on indirect effects, internal consistency, or traces from the very early universe that are still difficult to interpret. Even our observations of the early universe have limits. The cosmic microwave background is a rich source of information, but it does not come from the absolute beginning. Possible signals from even earlier epochs, such as primordial gravitational waves, are still being searched for with increasing sensitivity. The large-scale structure of the universe preserves some memory of early fluctuations, but over billions of years, gravity, galaxy formation, dark matter, and dark energy have all layered additional complexity onto the picture. Extracting clues about deeper origins from this data requires carefully untangling many overlapping effects. Another issue lies in language itself. Terms such as parent universe, baby universe, inside, outside, or birth easily sound like everyday stories, while the mathematics behind them is anything but ordinary. A branch of spacetime in a physical model is not like a child stepping out of a room, nor like a small sphere separating from a larger one. It may be a different causal structure, an extension of geometry, a quantum state within a broader framework, or a mathematical description of distinct space-time configurations. Everyday language helps make the idea accessible, but if it becomes too relaxed, it can quietly turn a careful model into a misleading image. Maintaining precision does not make this chapter colder. It creates a more stable place for understanding to rest. A black hole is strange enough without being exaggerated. An event horizon is deep enough without becoming a portal. The Big Bang is vast enough without being imagined as an explosion occurring inside pre-existing space. And a baby universe, if it is mentioned at all, is already remarkable simply as a possibility at the edge of quantum gravity. When each layer is placed correctly, the story does not lose its mystery. It only becomes less heavy because it no longer forces the listener to believe what has not been demonstrated. In the laboratory of the universe, black holes function like extreme natural experiments that cannot be recreated on Earth. No one can compress a star inside a laboratory to see how spacetime responds. No one can construct an event horizon and measure what lies beyond it with conventional instruments. Scientists can only observe real black holes in the cosmos, listen to their mergers, measure the light around their edges, build theoretical models, and test whether nature deviates in any measurable way from classical predictions. It is a slow process, but that slowness is part of what makes it reliable. Perhaps the quietest part of the problem lies in how science accepts not knowing. There is no need to fill the event horizon with a complete story. There is no need to turn every dark region into a promise of another universe. In the present stage of understanding, the more honest picture is layered. A solid body of data on the outside, powerful models that work up to the boundary, a deeper region where competing theories attempt to describe what happens next, and a set of bold possibilities waiting for observational hints. This layered structure is less dramatic, but it allows the topic to remain stable in the mind without drifting into exaggeration. The question of testability also changes how we read the entire narrative. Every black hole may hide another universe is not a conclusion that should be taken at face value. It is more like a guiding line into the deeper regions of physics, where what we know stops at the event horizon and what we do not know begins where general relativity and quantum mechanics have not yet found a common language. A title can open curiosity, but the body of the discussion must hold the reader with clarity. There is strong evidence for black holes, strong evidence for a hot, dense early universe, well-developed models of singularities, speculative ideas of bounces, and a very large gap before anything like a baby universe can be treated as reality. Within that gap, scientists search for indirect paths. Gravitational waves may carry information about space-time geometry before and after black hole mergers. Hawking radiation, if it is ever understood or observed in a more complete form, may connect to the question of information. Observations of black hole environments with radio telescopes continue to test general relativity in strong gravity regimes. The early universe may leave extremely faint signatures in the cosmic microwave background or in primordial gravitational waves. Each path is only a narrow beam of light, but in science, many narrow beams can gradually sketch the shape of a room no one has entered. The rhythm of black hole science does not need to be rushed. These objects existed long before humans gave them a name, and they will remain long after current generations of telescopes have been replaced. Data arrives slowly, models evolve step by step, strong ideas are refined or discarded depending on observation, and new questions appear along the way. In this process, the difficulty of verification is not a wall that makes everything meaningless. It is a reminder that some mysteries are not opened by quick answers, but by patience stretched across decades. Beyond that layer of difficulty, there remains a more immediate puzzle grounded in well-established physics. It does not require assuming baby universes from the start. It begins from a simpler and sharper point. Matter falling into a black hole carries information. Its shape, quantum state, composition, energy, and every physical detail are not merely secondary numbers. In quantum mechanics, information does not easily disappear from the world. A black hole, with its event horizon and Hawking radiation, turns that statement into one of the deepest tensions in modern physics. An object falling into a black hole does not carry only mass. It carries its own state, its internal structure, energy, motion, composition, and an immense collection of physical details that make it different from every other object in the universe. A cloud of gas is not the same as a stone. A star is not the same as a book. Two objects with identical mass can still differ in how their internal particles are arranged, in temperature, in motion, and in the long history that brought them to the edge of collapse. In modern physics, these details are not decorative. They are part of what is called the information of a physical system. When matter is still outside a black hole, that information is difficult to access, but not necessarily lost. A hot gas emits a spectrum of light. A star produces radiation, oscillations, chemical signatures. A collision leaves waves, heat, debris, or changes in surrounding motion. The data can be scrambled, mixed, and in practice almost impossible to reconstruct. But in the spirit of quantum mechanics, physical processes should not erase information in an absolute sense. The universe may make information extremely hard to read, but it does not easily allow it to disappear from the fundamental description of reality. A black hole pushes this idea into a far more extreme regime. From the outside, once matter crosses the event horizon, its detailed identity no longer appears in the black hole's observable properties. A large black hole, in its simplest description, is characterized mainly by mass, spin, and electric charge. The rich details of what fell in are no longer visible as shape, structure, or composition. Outside, only a dark region remains with a few global parameters, while the full microscopic history of the infalling matter disappears behind a boundary that does not return signals. For a long time, this created the impression that information was not destroyed, but simply hidden. If matter is inside the event horizon, it cannot be read from the outside, but in principle it might still be part of the interior description. The problem became more subtle when content reference, site, 0, index equals 0 showed that black holes, in a semiclassical picture, are not completely black. Quantum effects near the event horizon allow black holes to emit a very weak form of radiation, which over extremely long timescales leads to a loss of mass and energy. For astrophysical black holes, this process is far too slow to matter within the current age of the universe, but in principle it changes the entire structure of the problem. Hawking radiation is not like ordinary thermal light emitted by a hot object in any simple, directly observable sense for large black holes. It arises from quantum field theory on curved spacetime, where the black hole provides the gravitational background. In a simplified picture, Black holes have temperature and entropy, and they can slowly lose energy through the emission of quanta from the region near the event horizon. This should not be understood as matter escaping from inside after crossing the boundary. The process is more subtle, involving the quantum structure of fields in curved spacetime, where the notion of vacuum itself differs from that in flat space. The difficulty lies in the nature of this radiation. In its original formulation, Hawking radiation appears nearly thermal, meaning it does not seem to carry detailed information about the specific matter that formed the black hole. If a black hole grows by absorbing matter and then eventually evaporates completely into almost random radiation, it becomes unclear where the original information could be stored. It is no longer outside, because the matter has fallen in. It is no longer inside, if the black hole fully evaporates, and the remaining radiation does not obviously encode the detailed history. It is at this point that the black hole information paradox emerges. In this calm stretch of the story, a black hole begins to feel less like a void and more like a sealed container bound by deep physical laws. Outside the container, we can measure mass, spin, the size of the event horizon, the theoretical radiation, and the gravitational influence it exerts on its surroundings. Inside the container, the way information is stored or transformed is still not directly visible. That container does not necessarily destroy the story of what falls in. It may simply be rewriting it in a language that general relativity and quantum mechanics have not yet fully learned to read together. Once information is placed at the center of the discussion, the idea of baby universes becomes much more constrained. If a new spacetime branch is proposed in any model, it cannot simply be a place where all details are discarded, so that everything starts over. It must still respect deeper principles, conservation laws, entropy, quantum states, and the relationship between the event horizon and the interior geometry. A baby universe, if it is only a beautiful image, is not enough. It must exist within a framework that either resolves or at least does not worsen the tensions already present in black hole physics. Through the information paradox, black holes are no longer just an astrophysical mystery. They reach into the most fundamental structure of reality itself. How can space-time store information? How can time allow the past to be encoded? Can a boundary surface represent everything happening in a deeper region? These questions sound abstract, but they arise from something very concrete. Matter falls into a black hole. Black holes have entropy, and Hawking radiation prevents the story from remaining frozen forever beyond the event horizon. In this final part of the chapter, what matters is not the complexity of competing resolutions, but the steady pressure that black holes place on physics. They force us to move beyond the idea that everything simply disappears. They remind us that invisibility is not the same as non-existence, and that a silent region in observation can still hide a deeper order. From here, the story can continue toward ideas that have long appeared in popular imagination: wormholes, white holes, and strange connections in spacetime. But even when stepping into those regions, the same caution must remain. Mathematics may allow many doors, but nature chooses only a very small number of them to become reality. Of all the ideas associated with black holes, perhaps none is as widely known as the wormhole. From science fiction novels to films, it often appears as a shortcut through the universe, a passage where millions of light years can be crossed in a single journey. The image is so compelling that it is easy to assume wormholes are an awaiting astronomical discovery. The reality is far more subtle. What is interesting is that wormholes did not originate in fiction. Their roots lie in the equations of general relativity itself. When physicists explored different solutions to Einstein's field equations, they discovered that mathematics sometimes allows structures far stranger than everyday intuition would suggest. Spacetime is not only capable of curvature. In certain solutions, it can also be connected in special ways, as if two distant regions on a map were suddenly linked by a much shorter path. A common illustration is a sheet of paper. If 2 points lie far apart on a flat sheet, The shortest path between them lies across the surface. But if the sheet is folded so that the points come close together, a shortcut through the folded region can become much shorter. This is only a simplified analogy, because real spacetime is not a two-dimensional surface. Still, it captures an essential idea. Distance in curved geometry does not always behave like our intuition from flat space. Early investigations of wormhole-like structures appeared quite early in the history of general relativity. In 1935, content reference Waysit, 0 index égale 0 and content reference Waysit, 1 index equals 1, described a configuration now known as the Einstein-Rosen bridge. Mathematically, it resembles a connection between two regions of spacetime. However, this bridge is not a stable tunnel that a spacecraft could travel through. In the original model, it collapses too quickly for anything to pass through. This point is often overlooked in popular storytelling. The existence of a mathematical solution does not automatically imply the existence of a physical, traversable object in the universe. Physics contains many examples where valid equations describe structures that are not realized as stable configurations in nature. Wormholes, therefore, belong in their proper place, a mathematical possibility under certain conditions, not an observed astronomical object. In later decades, researchers continued to explore whether a more stable spacetime tunnel could exist. This line of inquiry led to an unexpected requirement. In most models, keeping a wormhole open requires matter, or energy, with properties very different from anything familiar in everyday experience. Calculations suggest that the throat of a wormhole tends to collapse under gravity. Preventing that collapse appears to require forms of energy with negative pressure or exotic energy density. This idea is often referred to as exotic matter. The term can sound like a mysterious substance hidden somewhere in the cosmos, but in practice it is a mathematical description rather than a known physical material. Certain quantum effects do suggest that localized regions with negative energy density can exist under special conditions, but extending such effects into a large, stable structure capable of holding a macroscopic wormhole open remains far beyond what is currently established. For this reason, most discussion of wormholes still remains in the theoretical domain. No astronomical observation has been accepted by the scientific community as clear evidence for the existence of a natural wormhole. Telescopes have detected countless black holes, galaxies, neutron stars, mergers, and other extreme phenomena, but no signal has yet forced physicists to conclude that a spacetime tunnel is actually present in the universe. This does not make the idea useless. On the contrary, wormholes play an important role as a theoretical tool. They help researchers probe the limits of general relativity, explore the structure of spacetime, and raise deeper questions about quantum gravity. In many cases, the value of a model does not depend on whether it exists in nature, but on whether it clarifies the underlying principles of the theory. In recent years, a particularly intriguing direction has linked wormholes to quantum information. In certain theoretical works, especially the idea known as ER equals EPR proposed by content reference, A site, 2, index equals 2, and content reference, A site, 3 index 3. Physicists explore the possibility of a deep connection between quantum entanglement and spacetime geometry. This is not a complete theory, and it remains under active investigation, but it suggests that wormholes are no longer confined to science fiction. They have entered the center of discussions about the nature of information and gravity itself. Importantly, these studies do not describe giant tunnels through which humans could travel. They usually involve very abstract mathematical structures that differ significantly from the cinematic image. The gap between a theoretical connection in spacetime and a traversable passage is still enormous. That gap is precisely why science maintains a cautious stance, even when the topic is highly captivating. Looking back at the broader narrative, wormholes appear as a side branch of a much larger story. Black holes lead to questions about singularities. Singularities lead to the need for a theory that unifies gravity and quantum mechanics. The black hole information paradox adds further pressure on existing frameworks. In the search for deeper descriptions of spacetime, wormhole-like structures emerge in equations as possibilities worth exploring. They are not endpoints. They are more like signposts, appearing along a road that physics is still trying to map at its deepest level. A familiar sense often arises when hearing about such hypothetical bridges across the universe. The feeling that distance itself suddenly becomes less meaningful. But the more profound insight lies elsewhere. Spacetime, usually imagined as a passive stage for events, may in fact have a far richer structure. It can curve, expand, ripple as gravitational waves, form event horizons around black holes, and in some models even allow unexpected connections between regions that appear completely separate. These ideas expand the universe in a very different sense, not by adding more galaxies or distances, but by revealing that the concept of space itself is far less simple than intuition suggests. Distance is no longer just a number measured in kilometers or light years. The geometry of reality becomes part of the story. Even so, observation remains the final guide. A beautiful idea does not automatically become reality. A mathematically consistent model does not automatically describe nature. Physicists can write many types of wormholes on paper, but the universe only realizes those that are physically allowed. The gap between equation and reality can last decades, sometimes generations. That patience is part of the beauty of science. It allows large ideas to be explored without turning them into premature conclusions. It preserves curiosity while staying anchored to data. Wormholes therefore occupy a unique position, widely known in culture, deeply studied in theory, but still unconfirmed in observation. Within the broader picture of black holes and possible deeper structures of spacetime, wormholes remain a faint branch on the map. They do not claim that every black hole leads elsewhere. They do not confirm that baby universes, if they exist, must be connected by such tunnels. They simply show that spacetime geometry may be far more flexible than everyday intuition suggests. And from these hypothetical tunnels, an even stranger idea emerges in theoretical physics. If black holes are usually regions where everything can fall in but nothing can return, some mathematical solutions suggest the opposite possibility, a region where matter can only emerge outward but cannot enter. In the language of relativity, this is known as a white hole. This concept is rarely discussed outside specialized contexts, but it has appeared in attempts to understand the full range of black hole solutions in general relativity. And from here, the story of what might lie beyond extreme regions of spacetime takes an even more unusual turn. Time in everyday life almost always seems to move in one direction. Smoke slowly dissolves into the air, a cup of hot water cools down on a table, and light from an ancient star continues its journey into the dark. A falling glass shatters on the floor, but its fragments never quietly gather back into a perfect cup and return to the edge of the table. These processes are not dramatic, yet together, they create a familiar sense that nature has a preferred direction of flow, a quiet arrow we call the direction of time. This arrow is what makes white holes such a strange and unsettling idea. In the equations of general relativity, certain extensions of black hole solutions can produce a kind of time-reversed counterpart. A black hole is a region where matter and light can fall in, but cannot send signals back out. A white hole, in that mathematical picture, behaves in the opposite way. Matter and light can emerge from it, but nothing can enter. It is a striking symmetry, almost like two mirrored sides of the same drawing. Yet the real universe is not required to realize every symmetry allowed by equations. Black holes have traveled a long path from mathematics into observational astrophysics. At first, they appeared as unusual consequences of general relativity. Over time, indirect evidence became increasingly strong, stars orbiting an invisible mass at the center of galaxies, hot gas glowing intensely before crossing into dark regions, gravitational waves from mergers, and finally the shadow-like images reconstructed by global radio telescope networks on Earth. These observations do not reveal what lies inside the horizon, but they are sufficient to make black holes real objects in physics, not just abstract solutions. White holes, by contrast, have not followed this journey. They remain primarily in the realm of mathematical extensions and theoretical speculation. In the idealized picture, they resemble a film played backward. Instead of matter falling inward and disappearing behind an event horizon, matter appears from an extreme region and moves outward. Such behavior can be written consistently in equations, but turning it into a stable, naturally formed object in a noisy universe is an entirely different challenge. Here, entropy becomes an invisible but central character. In everyday experience, entropy appears in very simple ways. Heat spreading from a warm cup of tea, scent dispersing through a room, sand being reshaped by waves, dust quietly settling on objects left untouched. Ordered configurations tend to spread out rather than spontaneously reassemble. A white hole, in its time-reverse black hole form, seems to require an extraordinarily special initial arrangement, so precise that even the smallest disturbance would destroy the idealized picture. This does not make white holes meaningless. Instead, it highlights how far equations can extend beyond intuition. Even without observational evidence, such structures help physicists probe the limits of general relativity and explore what might happen when spacetime is pushed into extreme regimes. In some approaches to quantum gravity, where classical singularities may be replaced by finite transitional regions, white holes can appear as possible outcomes of certain hypothetical processes, not as observed objects, but as ways of extending the story of spacetime beyond classical collapse. These ideas remain firmly within theoretical boundaries. No astronomical observation has identified a black hole transitioning into a white hole. No signal from the sky has forced the scientific community to accept white holes as real astrophysical objects. Bright cosmic events such as supernovae or gamma-ray bursts already have well-studied physical explanations and do not require invoking white holes. A dramatic appearance of light or energy alone is not enough to justify such an interpretation. For this reason, white holes are best understood as mathematical reflections rather than confirmed features of the universe. They emphasize the difference between what equations allow and what nature actually realizes. Mathematics can generate many possible spacetime geometries, but only a subset of them are selected by physical conditions such as stability, formation mechanisms, and the arrow of time. Some structures migrate from paper into the sky. Others remain as conceptual tools for probing deeper principles. Within the broader narrative of black holes, white holes serve an important clarifying role. They remind us not to confuse mathematical symmetry with physical existence. Wormholes, white holes, and hypothetical baby universes all arise from different corners of theoretical physics, each with its own assumptions and motivations. They may intersect in certain discussions, but they do not automatically imply one another. Keeping these distinctions clear allows the story to remain scientifically grounded rather than drifting into speculation. There is a quiet kind of beauty in leaving white holes in this intermediate state. They do not demand belief, nor do they close the door on curiosity. They simply show that spacetime in Einstein's equations is richer than everyday intuition suggests, while also reinforcing that observation remains the final judge of reality. Through a cleaner lens, without exaggeration, the genuine structure of the universe often appears even more striking. After such time-reversed horizons and unobserved counterparts, the narrative can return to firmer ground. Black holes themselves still leave measurable traces, light bending around their edges, gravitational waves carrying the imprint of mergers, and stellar orbits revealing hidden masses at galactic centers. Even if nothing escapes from within the horizon, the outside world continues to speak clearly. From those signals, physics continues its slow and careful work testing ideas about singularities, quantum effects, information, and the possible extensions of space-time beyond what current theory can fully describe. In the most grounded part of the story about black holes, what remains most reliable always returns to what the universe reveals on the outside. A region that does not send light back does not mean all traces are erased from the sky. Before matter crosses the event horizon, it can still heat up, swirl around, emit radiation, and reshape the space-time around it. Light passing nearby is still bent. Stars in the vicinity still move under the influence of an invisible mass. And when black holes merge, space-time itself can ripple, sending gravitational waves across vast distances. Because of these signals, the science of black holes does not begin by looking inside the horizon, but by reading what the horizon does to everything around it. The shadow seen in images from the Event Horizon Telescope is not a photograph of the interior of a black hole, but a map of how light behaves around an extremely strong gravitational field. The stars orbiting Sagittarius A times do not fall directly into darkness, yet their motion reveals a vast concentration of mass confined to a very small region at the center of the Milky Way. Gravitational waves from mergers do not describe what happens inside the horizon, but they carry the imprint of two black holes as they spiral together and settle into a new, stable object. Across all of these signals, general relativity continues to perform remarkably well. The size of the shadow matches predictions. The waveforms of gravitational waves align with simulations of merging black holes. Stellar orbits near galactic centers are consistent with the presence of a compact, extremely massive object. These results do not mean the interior is fully understood, but they establish a very solid foundation. Any new model involving singularities, bounces, white holes, or baby universes must first reproduce everything we already observe on the outside. Only then is it allowed to modify what happens deeper in. This is how science approaches mysteries without exaggerating them. A new model is not judged only by how imaginative it is. It must leave traces somewhere, even if those traces are extremely subtle. It might be a slight correction in the final stage of gravitational waves after a merger. It might be a refined prediction about how event horizons behave. It might appear in black hole evaporation in theoretical descriptions, or in the relationship between entropy and information. It might even emerge indirectly from the early universe, where extreme conditions could leave faint imprints in the cosmic microwave background or in large-scale structure. These signals are not easy to extract. The universe does not present answers as clear sentences written across the sky. Data is often weak, mixed with noise, and open to multiple interpretations. A small fluctuation in gravitational wave data could come from the source itself, from environmental effects, from detector limitations, or from new physics. An unusual pattern in early universe observations could be a real imprint or a statistical or modeling artifact. Because of this, major ideas must pass through many layers of careful testing before they are taken seriously. There is a very slow rhythm to this process. Astronomers do not simply look at a single image and draw conclusions. They measure again, compare, simulate, eliminate alternatives, wait for more data, and check whether a model remains consistent across different types of observation. Black holes became established in exactly this way. First, as mathematical solutions, then as candidates in X-ray sources, then as objects influencing stellar orbits, then as sources of gravitational waves, and finally as shadowed regions reconstructed by global telescope arrays. Each layer did not stand alone. As a revelation, it stacked together into a picture that became increasingly difficult to dismiss. Any deeper model of black holes must follow a similar path if it is to move beyond speculation. A bounce scenario must not only avoid singularities mathematically, it must also remain consistent with everything observed outside the horizon. A transition from a black hole to a white hole must not only be mathematically possible, it must also fit within known limits from Hawking radiation, gravitational waves, and black hole lifetimes. A baby universe idea must not only be geometrically elegant, it must also confront the demands of information, entropy, and observational consistency. In this regime, caution does not diminish the subject, it deepens it. A black hole does not need to be a confirmed gateway to another universe in order to be extraordinary. The very fact that it forces us to measure light near the edge of darkness, listen to ripples in space-time, and test our deepest theories in the strongest gravitational fields already makes it one of the most important objects in modern physics. The unknown does not sit separate from data, it is surrounded by it, like deep water inferred from the motion of waves along the surface. Radio telescopes refine the image of the shadow. Gravitational wave detectors listen to more mergers with greater sensitivity. Stellar observations track motion near galactic centers with increasing precision. Cosmological surveys map the early universe in finer detail. Each of these is a small light placed around the edge of a vast, unseen region. With time, these measurements will only become sharper. Future observatories may reveal finer structure in black hole shadows. Next-generation gravitational wave detectors may capture mergers at greater distances and with richer detail. Improved monitoring of galactic centers may track matter and motion closer to the horizon. Cosmological missions may probe early universe signals with unprecedented sensitivity. None of these guarantees a dramatic breakthrough, but together they steadily narrow the space in which theoretical models can hide. This is especially important for bold ideas. When data is scarce, many models can coexist. As data accumulates, some are ruled out, some are refined, and some become more compelling because they explain multiple phenomena at once. Science rarely advances through a single decisive observation. It progresses through the slow accumulation of small constraints that gradually reveal which descriptions of nature remain viable. In the story of black holes, the testable part of reality still lies mostly outside the event horizon. This is not a limitation, it is a safeguard. The interior cannot be freely filled in with imagination. It must be inferred from what the exterior allows, from the consistency of theory, and from tensions between general relativity, quantum mechanics, and information. The more a model claims about the unobservable region, the more carefully it must respect what is already known. These boundaries do not shrink science, they mature it. There are moments when saying, "We do not yet know," is not failure, but precision. Black holes once lived entirely in that unknown region before gradually becoming observable through indirect evidence. Gravitational waves were once purely theoretical before becoming measurable signals. What lies deeper still may take longer, or may require a fundamentally new way of thinking about space-time itself. What remains constant is the requirement of traces, not large traces, not obvious ones, but subtle differences in light, motion, waves, background radiation, and mathematical consistency. A completely disconnected baby universe that leaves no imprint in our observable reality would remain outside the reach of empirical science. But any model that produces even indirect, testable consequences can still play a role in guiding the search for a deeper theory. This distinction brings the entire question back into focus. A black hole may hide something profound, but not everything we can name deserves to be treated as physically real without evidence. Darkness alone is not proof. Elegant equations alone are not the sky. Between them lies the working space of science, measurement, comparison, simulation, refinement, and patience. When all speculation settles, the black hole remains what it has always been in the language of physics, not a simple abyss, but a long-term test of how we understand the universe. Inside, silence persists. Outside, the universe continues speaking in faint but consistent signals. Rings of light, stellar orbits, gravitational waves, and subtle shifts in data. These are not full answers, but they are enough to guide the next step forward, without rushing beyond what nature is willing to reveal. After many layers of observation, models, and hypotheses, black holes still preserve a very particular kind of silence. Not the silence of emptiness, and not the silence of a mystery exaggerated into something overwhelming, It is the silence of a real boundary where light does not return, where direct signals can no longer reach an outside observer, and where even our best physical theories begin to touch the limits of their own completeness. The most certain part of the story is not small. Black holes are no longer just theoretical images. They leave traces in stellar orbits, in hot accreting gas, in reconstructed shadows, and in gravitational waves propagating through spacetime. The event horizon, in general relativity, is not a physical surface, but a deep causal boundary in spacetime. Matter approaching a black hole can heat up and brighten the surrounding region before crossing beyond view. When two black holes merge, they can set spacetime itself ringing, producing ripples so faint that they can still be measured by detectors on Earth. These belong to the solid foundation of modern physics. Alongside this foundation are regions of powerful but incomplete modeling. The singularity, in the classical description of general relativity, should not be understood as an observed object at the center of a black hole. It is better seen as a sign that the theory is being pushed into a regime where it can no longer describe everything consistently. Hawking radiation, black hole entropy, and the information paradox show that black holes are not only an astrophysical subject, but also a place where quantum mechanics, thermodynamics, and gravity meet in a profoundly difficult problem. Ideas such as bounces, white holes, wormholes, or baby universes exist further out, in a theoretical landscape still being explored, where mathematical beauty must wait for experimental scrutiny. Keeping these layers separate is what makes the topic scientifically trustworthy. If they are blended too quickly into a single story, black holes become an overly convenient symbol, a gateway, an escape route, a birthplace of other universes, a universal answer to mystery. But the universe does not need to be exaggerated in order to feel profound. It is already profound when each layer carries its own degree of certainty. Some layers are directly observed. Some are strongly inferred from well-tested theories. Some are actively being explored in competing models. And some remain distant possibilities, kept alive because they sharpen the questions, rather than because they are confirmed realities. In the slow rhythm of science, not knowing is not a void that must be filled immediately. It is more like a dark ocean beyond the reach of a lantern, still present, still deep, but not yet ready to be fully mapped without sufficient data. Humanity has lived with such regions of uncertainty many times before. Before the shadow of a black hole was imaged, there were equations, stellar orbits, and indirect clues. Before gravitational waves were detected, there were predictions spanning a century. Before cosmic expansion was understood, the night sky appeared static and unchanging. Each time new data arrived, the universe did not become less mysterious, it simply shifted its mystery one level deeper. Black holes continue to do the same for modern physics. They do not only ask where matter goes when it falls in, they expose the limits of how we currently understand space and time. They raise questions about information without turning them into simple puzzles. They force quantum gravity to confront a regime where large mass, extreme density, and causal boundaries all converge. A future theory may show that classical singularities are replaced by finite structures. Some present models may be ruled out. Ideas about baby universes may be revised, narrowed, or replaced by more precise descriptions. All of these possibilities belong to the natural way science evolves, not to failure. There is a quiet stability in allowing questions to remain exactly where they are. A black hole may not hide another universe. It may simply conceal a region of physics that current theories cannot yet describe in full. But even this more modest possibility is already profound. If the interior replaces singularities with some unknown quantum structure, that alone would represent one of the deepest advances in our understanding of nature. If information is preserved in ways not yet fully understood, black holes will still reshape our view of reality. And if more speculative ideas turn out to be partially correct, then the story of the universe becomes even larger than it already appears. What matters is that we do not need to choose between rigidity and exaggeration. A scientific narrative can remain between those extremes. It can state clearly what is known while preserving the depth of what is not. It can avoid overreach without losing wonder. It can allow the listener to rest inside the scale of the universe, rather than forcing constant answers to questions that are not yet ready to be answered. Black holes are especially suited to this balance because they are objects that are simultaneously certain in their observable effects and deeply uncertain in their interiors. Looking back over the entire journey, the original question gradually becomes gentler. Could every black hole hide another universe? Is no longer a forced conclusion, but a way of approaching the edge of current understanding. Ahead of that question are real black holes, real data, real event horizons, real limitations of general relativity, real tensions with quantum mechanics, and real hypotheses under active investigation. Behind it lies a region of the unknown, where the answer may be simpler than imagined, or far deeper than any language we currently have can express. Inside the darkness of black holes, science learns something subtle. Not seeing something does not mean there is nothing to understand. There are regions that return no light, yet still shape orbits, bend trajectories, ripple spacetime, and test our theories to their limits. Some mysteries do not need to be amplified to become vast. They only need to be placed correctly between data and limitation, to reveal that the universe is always deeper than what light alone can tell. And perhaps that is what makes black holes one of the most beautiful images in modern science. They are not merely darkness. They are places where light stops at a boundary, while human curiosity continues to move along the edge slowly, carefully, reading every faint trace. Not to turn every unknown into an answer, but to learn how to live with a universe that is still unfinished in our understanding. By the end of the journey, what remains is not a definitive claim that every black hole contains another universe. What remains is a quieter way of seeing darkness. Some darkness is simply absence of light, but some darkness is the edge of knowledge itself, where science does not stop in certainty or fear, but pauses, measures what can still be measured, and then continues forward with calm, steady questions. Perhaps the most gentle thing black holes leave behind is not a definitive answer, but the sense that the universe still has very deep boundaries. They do not appear as loud structures, nor as bright walls or mysterious gateways. They exist quietly within the fabric of space-time itself, strong enough that light cannot return, powerful enough to change stellar orbits, heat surrounding gas, and send ripples through space-time, yet sealed in a way that prevents the deepest part of their story from being directly told to us. When people think about black holes, they often begin with the idea of an ending. A star exhausts its fuel, collapses under its own gravity, and leaves behind a region of darkness from which not even light can escape. But as we move deeper into the science, that image expands. A black hole is not only a place where matter falls inward, it is where general relativity reveals the extreme power of space-time geometry itself. It is where quantum physics raises questions about information. It is where thermodynamics finds entropy associated with a horizon. And it is where our most advanced physical theories meet boundaries they have not yet fully resolved. From the outside, black holes have become part of the observable universe. Stars near the center of the Milky Way do not need to see the dark object directly to reveal it; their orbits already do. The bright rings around the shadow do not require access to the interior to show how light is bent by extreme gravity. Gravitational waves do not need to reveal the event horizon itself to tell us that two black holes spiraled together and merged. Through these subtle and persistent traces, the universe confirms that these dark regions are not just mathematical ideas, but real physical objects. The unknown lies deeper. The classical singularity is not an observed object at the center of a black hole. It is a sign that the current theory is being pushed beyond the range where it can describe reality consistently. Ideas such as bounces, white holes, wormholes, or baby universes emerge when physicists try to understand what spacetime might become if infinity is not the final description of nature. Some of these ideas are mathematically elegant. Some help illuminate paradoxes about information. Some may eventually be replaced as theory and data advance. Their value does not depend on whether they are true, but on how clearly they sharpen the questions. So can every black hole hide another universe? The honest answer must remain open. At present, there is no observational evidence confirming such a thing. Black holes are not proven gateways to other universes. Baby universe scenarios, where they appear in some theoretical models, remain speculative and carefully constrained within mathematical frameworks, rather than established physics. Yet even the deepest interior of a black hole is not a place where physics has finished speaking. At the very boundary where light cannot return, our best theories are still learning how to describe themselves. This openness does not weaken the story. It strengthens it. Some areas of science are beautiful because they are nearly complete. Others are beautiful because they reveal how knowledge expands at its own edge. Black holes belong to the second category. They are real enough to measure, yet deep enough to resist full description. They allow us to stand at a boundary without needing exaggeration or fear, only careful attention to what the universe still allows to escape outward. In this quietness, the darkness of black holes changes its meaning. It is no longer simply the absence of light. It becomes a boundary of understanding, a place where direct observation ends, and inference, modeling, and increasingly precise measurement must take over. It reminds us that what matters most is not always what shines brightest. Some truths appear only as subtle deviations in light paths, slight changes in stellar motion, or faint ripples in spacetime that took an entire century to learn how to hear. If one day a deeper theory explains the interior of black holes without requiring baby universes, the story will still be profound. If information is shown to be preserved in ways more subtle than we currently understand, black holes will still reshape our view of reality. And if some of the more speculative ideas about new spacetime branches survive future tests, the universe will become larger, not only in distance, but in the very structure of space and time itself. Whatever the final answer turns out to be, black holes will have already accomplished something remarkable. They have turned darkness into a place where science learns to ask better questions. Out there, black holes continue to sit at the centers of galaxies, in the remnants of massive stars, and in binary systems slowly spiraling toward merger. Around them, light continues to bend. Matter continues to heat up before crossing the final boundary. Space-time continues to ripple from distant collisions. The deepest interior remains silent, but that silence is no longer an empty wall. It feels more like a pause in the universe's music, where the next notes have not yet been written in a language we fully understand. Thank you for spending this time with Sleep Gravity, exploring the deepest dark regions of the cosmos. As the night continues on Earth, perhaps we can hold on to a gentler thought: darkness is not always emptiness. Sometimes, it is simply where our understanding pauses for a moment, breathes, and then quietly prepares to open another question even deeper than before.